Hi, everybody. My name is Saurabh Savdani. I'm a grad student in Georgia Tech, and I'm going to talk today about the fully dynamic algorithm for the densest subgraph problem. And this work is joint with Junsing Wang from CMU. Right. So the plan for today is I'm going to introduce dense subgraphs, dynamic algorithms. I'm going to talk about why each of those are important. After that, I'm going to formulate our densest subgraph problem via its dual linear program and see that it is actually a load balancing problem. And once we formulate it that way, we're going to get to the update algorithm and see how it works. All right, so let's get into the introduction. Dense subgraphs, they're exactly as the definition suggests, they're subgraphs of a massive network which are much denser than the network itself. So in this example, all these blobs are dense components, and it is usually in our interests in a lot of applications to extract these dense parts of networks. Right. So one motivation for this kind of algorithm to find dense subgraphs. This is a very generic one. If you think of vertices as entities and edges denoting strong correlations between these entities, then basically a dense subgraph is a highly correlated subgroup. If you want specific examples of this, if you think of gene correlations, a dense subgraph expresses a co-expression module, or basically something which actually corresponds to a particular characteristic. And similarly, in stock correlations, these dense subgraphs are useful to analyze market dynamics, right? Another example of an application of this kind of dense subgraphs is if you have a graph which denotes page-like data, where pages link to each other, and especially dense component can reveal an artificial attempt to inflate the page rank. Right. Another possible example of an application is, say, in Twitter data, if we have nodes which donate entities which appear in tweets, and an edge is to denote when two entities co-occur, like a hashtag and an image and something like that. And once you form a dense subgraph of these co-occurrences of entities, what you get is a news story. Right. So once we have some idea of how this notion of dense subgraphs is useful in practice, let's get into how we literally define density in our graph. So the definition we'll be working with is the average degree, or essentially twice the average, half the average degree. So here it is basically for any subset, the density is the number of edges divided by the number of vertices in the subset, right? So the densest subgraph essentially would be the subgraph which maximizes this quantity, right? So basically the subgraph with the maximum density, and the density of this densest subgraph is something we'll call the maximum subgraph density. So essentially all we're trying to maximize is this quantity E of S divided by S. There should be a mod on the numerator as well. All right. So here is some algorithms which exist to find the densest subgraph in the static formula, where you've given an entire graph and you want to find it. The exact algorithm was given by Goldberg in the 80s, and it's a reduction to max flow. Charikar came up with a very fast algorithm, but a theoretical guarantee is only a half for this greedy algorithm. And recently, maybe not that recently, Bahmani et al. Gave a similar kind of idea as to what we'll talk about, is where they solved the dual of the problem. And what they noticed is the dual is a linear program with only positive, only non-negative entries. And they solve this linear program, and this gives a near linear time algorithm for the problem. All right. But what we're interested in is in dynamic algorithms. And why is that? because most of the graphs which we work with in the real world are constantly changing, and essentially they're huge networks, and what we don't want to do is anytime there are small changes in this network, we don't want to recompute the entire algorithm from scratch. We want a quick update of our solution, right? So what our goal is to make efficient data structures such that if we already have an existing solution, then you can just update it quickly using this data structure, right? Much faster than redoing the algorithm would be. All right, so our goal for today is a fully dynamic algorithm for a densest subgraph problem, and what that means is you should be able to do these three operations. You should be able to insert an edge, delete an edge, or at any point you should be able to query the maximum subgraph density in the graph up to some 1 plus epsilon factor error. Right? That is our goal for today, and ideally this should be much smaller than linear time, and as in most of dynamic algorithms, our desired runtime is in polynomial in log n and in epsilon to the minus 1. All right. So here are some existing algorithms for this problem, for the dynamic problem. There's a 1/4 approximation algorithm which works in the required runtime and is amortized. There's a similar algorithm which is a bit faster but has the caveat that only random deletions are allowed. What we do is uh, we make the approximation factor as good as it can be for approximations, and we still and we even improve upon the amortization. What we have is a deterministic worst case runtime of at most polylog and poly in epsilon minus 1, right? That's what we're going to talk about today. All right, so the first thing we'll do is we'll formulate the problem as a linear program, and then we'll talk about how we go ahead and solve it, right? So consider this formulation of the problem. Essentially, ye and xv denote an edge actually being picked in the solution or a vertex actually being picked. Notice that an edge is only picked if the vertex, if both its endpoints are picked. Here, e is uv, and what we're trying to maximize, as we defined earlier, is in a subset of selected vertices, what is the summation of the of the number of edges divided by the number of vertices, right? So clearly this initial formation is not a linear program, so we use a linear program relaxation. So we allow these variables to be any real numbers, and this denominator, we kind of normalize it by allowing it to be at most 1. And now we have a linear program formulation for this, and it turns out that this actually exactly formulates the densest subgraph problem. And this was proved by Charikar in his paper, where he also gives the greedy algorithm for the problem. So essentially, all we need is to find a solution for this primal problem. But what we'll do today is we'll actually formulate the dual and try and solve that problem, right? So given this is our primal, here is the dual which you can find. If you associate the variable d with this and feu and fev with this, the first kind of equation or inequality, then we end up with this. And the way we'll visualize this dual problem is as follows. So let feu, imagine it is some kind of load that the edge e assigns to its endpoint u. And what we want to bound is this total load on vertices. No vertex should have load more than d, and we want to minimize this d, right? So try and think of it another way. The first thing that we can do is we don't need to have a greater than equal to inequality here. We can replace it by an equal sign. There is no value for feu plus fev to be greater than 1. Secondly, notice that all we did was say that this is the load on a vertex, and we wanted to make sure all of them were at most d, and we were minimizing d, which pretty much means we're minimizing the maximum load on any vertex, right? So the goal, now you can think of each edge having a load of 1, and what we're going to do is assign this load fractionally to both endpoints. And once we assign this load fractionally to both endpoints, our goal is to minimize the maximum load on any vertex. All right? Cool. So now we can get into the actual algorithm that we use, the update algorithm. So let's get into it, right? As we said, this is our dual LP. We have a load of 1, which we want to distribute among its endpoints, and we want to minimize the maximum load over all vertices, right? Now consider some edge E, which is UV, and suppose it assigns some non-zero amount of load to one of its endpoints, say U, and it so happens that U overall has higher load than the other endpoint V, right? In this case, there is a simple way to make this load assignment slightly more balanced, right? At least a little bit more. Because LU is definitely greater than LV, what we can do is you can just transfer some of E's load to V, from U to V, and we're only going to minimize our objective. We're only going to decrease our objective, and so we'll only do better. All right, so there is, anytime this condition happens where FEU is greater than 0 and LU is greater than LV, there is an easy way to transfer some load and make the solution better. All right, so clearly this gives some kind of local optimality condition, and we'll phrase it like this. So anytime FEU is greater than 0, we say that this edge is locally optimal if LU is less than or equal to LV, which means that we can't just transfer some load to V and make the solution better. All right, and we are still maintaining the fact that the total load of an edge is 1, and it assigns its load to both endpoints, and this is something we'll call the local optimality condition. Note that we're only trying to get an approximate solution, and a 1 plus epsilon approximate solution to the problem, so we'll adjust our condition a little bit. We'll allow for a slack of eta. This eta can be any number for now. Think of it as any number, and we'll formulate eta as in how we require it for our solution, right? So an eta approximate local optimality condition is when each edge assigns its load to both endpoints, load of 1, and if any endpoint receives some load from the edge, then it cannot be too much greater in total load than the other endpoint, right? That's the local optimality condition. And what we show is actually this kind of local optimality actually implies global optimality, right? So eta approximate local optimality makes sure that the maximum load that you get while satisfying local optimality cannot be more than 1 plus epsilon times the optimum. All right, and what is the relation between epsilon and eta here? It's a simple direct relation. If we know the kind of epsilon that we want, and we have some kind of approximate value for our optimum solution at that point, then we can formulate our eta, which we want to establish as a local optimality condition, right? So if we know a desired epsilon and a constant approximation to OPT, then we can get eta, and once we have eta, we can try to enforce this eta approximate local optimality condition, right? Right. So one small change we're going to do now is try and make the problem easier, in the sense that one edge is assigning its load partially to both endpoints, we will make sure that okay, what we'll do is we duplicate each edge enough number of times. Note that here enough is log n to the epsilon squared times. And now if you notice that if we can do that, then eta can only be an integer, which means that it's totally okay in our optimality condition to be off by 1 at least, which means that there's no need for any edge to assign itself fractionally. It can now assign itself completely to one side or the other. All right. And once we can assign an edge completely to one side or the other, we can visualize it as giving a direction to the edge, right? So assigning an edge uv towards u, we visualize it as giving a direction towards u. And now the problem is, the same problem becomes assign directions to each edge such that the maximum in degree is minimized. Note that all we did is, instead of assigning an edge fractionally to both endpoints, all we did is we broke it up into many parts so that each of these parts now only needs to be fully assigned to one endpoint or the other. Okay, so now we have the problem of minimizing the maximum in degree and assigning directions to make sure this happens. And the underlying system we have is we are adding edges and deleting edges. All right. So let's go ahead and do that. Again, we want to maintain this local invariant at all times, and we proved that maintaining this local invariant actually also maintains the global near optimal solution. Right? So what we want to do is, once we have this kind of invariant, suppose we insert an edge w to v, right? What could happen here is the load of v could increase and it could break this condition. All right. So suppose earlier when this condition was true, but it was not tight, there was nothing to worry about. Adding one more edge is not going to break the condition. But if it was already tight, it was at the border of this inequality. Now adding another edge is going to make this local condition false. So we need to fix it, right? And the way we fix it is we now want to flip this edge uv such that the load of v goes back to what it was earlier, but now the load of u increases, right? So does that suffice, flipping one edge? No, because what you've done is flip this edge over uv. Now the edge is directed towards u, which means the load of u is increased, which could break some other inequality somewhere, right? And the same thing happens in deletions, right? Suppose we already have this edge w to u, and if we delete it, it could possibly break the invariant if it was a tight edge, if uv was a tight edge. And to fix that, what we can do is we can flip this edge uv again such that it directs towards u, but this will decrease the load of v, and again that can cause an avalanche of again invariants being broken everywhere, right? So how do we fix this? Okay, I mean, one way you could say is that each flip could cause many more flips. So how many more flips can there be at most, right? And we show that there are not going to be that many flips, right? So the maximum load in a graph is always around the optimum. If we maintain our solution, then we know that we are within 1 minus epsilon or 1 plus epsilon of the optimum. And note that each tight edge actually is required to have this gap of epsilon. Okay, it has to be equal. LV minus LU has to be eta, sorry, not epsilon. And when that happens, so since the maximum load is around opt and the minimum load is around zero, the longest chain of these tight edges can only be of length log n over epsilon squared. This is from the definition of eta. And once we have this longest chain of tight edges is at most this, we know that the flips are always going to be bounded by this number, right? And And so this solves the problem of having to deal with too many flips, because each time you only flip a chain of tight edges, and and since we bound it, it's not a problem anymore. All right. Okay. So one additional part still remains. Note that as our algorithm goes on, the opt changes, and so when opt changes, eta changes, and so on. But until now, we haven't worked towards solving this kind of issue where opt and eta are dynamically changing. All right. So yeah, notice that if eta becomes too small, then the number of flips is way larger than this quantity, and if eta becomes too large, then we no longer are guaranteed a good approximation of the problem. So how do we deal with this dynamically changing eta is in a very brute force manner. You just make log n data structures such that each one corresponds to a particular approximate value of opt. All right. So if opt is say 2, then we deal with the data structure. Opt is approximately 2, then we deal with the data structure corresponding to that value. All right. And according to the value of opt, we set eta I. And once eta I and opt are fixed for that data structure, we only need to worry about that data structure. And as soon as the opt changes, we move and worry about the other data structure. And whenever we're querying the max subgraph density, you only query the right one. All right. So that solves that problem. The total runtime for this is the number of data structure copies we made, the number of duplicate edges we created, by splitting into many parts, and the max flips per update, and lastly, the cost of each flip. This is something we didn't talk about, but it is also bounded using simple data structures. So overall, we get log to the 4n and epsilon to the -6. All right, just to recap, the load balancing problem is the dual of the densest subgraph problem, and our goal is to minimize the maximum load where each edge has a load of 1, and this can be converted to the edge orientation problem. And lastly, what we only want to do is maintain the local invariant at all times, and each insertion can cause a flip, and each deletion can cause a flip, and each update can only cause a few flips. That completes the algorithm. Thank you.